Hello everybody. So now we are going to start with the first method that we are going to use to predict or get an idea of the shape of the equation that we can use to calculate the mass transfer coefficient. And this method is called dimensional analysis coupled with experiments. And I think this method is is a common method that has been discussed in fluid mechanics and heat transfer courses for those who have taken these courses before. I'm going to go through the steps of this dimensional analysis and to get the output out of it. But what I want to focus on in this video is the merit of this method, why we bother to do this, and what is the point of doing this dimensional analysis. And I believe this is pretty important because in many cases people just go directly to the method of the dimensional analysis without taking time to talk about the reasons of taking this route. So to start, let's first agree that we know that in case of forced convection, we have many factors affecting the mass transfer coefficient. As we said, the mass transfer coefficient takes into account the geometry, takes into account the flow properties and the fluid properties. So the parameters that cover all these three categories are the L, which is the characteristic length, the velocity, density, viscosity, and diffusion coefficient. So these are the 5 parameters that we can use to calculate the or that affect the mass transfer coefficient. We don't know how they affect it. Does mass transfer coefficient increases if they increase, decreases as they decrease? This is something that we don't know, and that's why we need to do experiments to study the effect of each one of these parameters on the mass transfer coefficient. And this is takes us back to the name. It's dimensional analysis coupled with experiments. So what we are gonna discuss here is the steps that you would do as an experimentalist who is doing the experiments to find out the effect of each one of these parameters on the mass transfer coefficient. And if you think about this, let's say in our case I have 5 parameters and I want to study the effect of each parameter. So simple logic says that I am going to first keep all the parameters constant except one. So let's say I want to measure now or study the effect of characteristic length on the mass transfer coefficient. So I am gonna keep everything constant: the velocity, density, viscosity, diffusion coefficient, and change L so that the change in mass transfer coefficient is only due to the change in L. So I keep away any other changes, but only the effect of or the change due to the change in L. So this is simple logic. So you keep everything constant, you change L many times. So what I'm suggesting here is 10 times, and this is not right, and this is a very, very small number. Usually in experiments people do 30, 40, 50, maybe more experiments, so that you have a lot of data points. So this will reduce the experimental error, reduce the any errors that might happen due to any of reasons of human error, experimental error, whatever the error. So we should generate a lot of data points so that we can have reliable results. But let's say for the sake of argument that we are gonna keep them only 10, just for the sake of argument. And then for each one of these runs, I change L, and then I measure or calculate Kc, and then I repeat it for the rest of the parameters. So I'm doing 10 experiments for L, 10 for V, 10 for ρ. So this is 10 multiplied by 5 equals 50 experiments. So the output of my experiments would be a tables like this and this. For the first table, I'm keeping V, ρ, mu, d constant, and I'm changing L, measuring Kc. The same for V, everything else is constant, and so on until I finish the 5 parameters. So I have 5 tables. Each table contains 10 data points, if 10 is okay. And then we have all our data points. So this sounds nice and sounds like a good approach, but If you think about this or take some time to think about this, there will be some questions that will jump into your mind, and they're very, very logical and legitimate questions. So the first question, let's say we agreed that we are going to keep v, rho, mu, and d constant, and we are going to change L. But the question is, what are the values of v, rho, mu, d that you are going to keep constant? Are you going to keep the velocity equals 1 meter per second, 2, 3? The density, you are using water, so you're using density of 1000, or you're using an oil with density 800. The diffusion coefficient, what's its value? So the question is, what is the basis on which you decide that these values are the constant values that you want to do? And how can you make sure that if you change these values to any other values that are constant as well, you're going to keep them constant but with other values, that this will not affect the results that you have? So perhaps it's very, very, very probable that the values that you get in this table are produced in this way because the values of v, rho, mu, and d that you have and you're keeping constant led to these numbers. So if you put them in another with other value, this will have an effect on the mass transfer coefficient values, and that's why this is something that needs to be tested. So we have to take this into account. So I'm gonna repeat what I'm doing, but I'm gonna do one bigger loop. So this is gonna be an internal loop to fill this table, and I am gonna change the values of rho, v, mu, and d, do 10 experiments, and then put another value of rho, v, mu, and d, and that's what we should get. That we will have more columns for the same parameter. In this case, I'm not changing the parameter. I'm keeping everything the same, but I am doing the same experiment for different constant values of rho, v, mu, and d. If we agree that 10 points is okay, so I'm gonna repeat this 10 more times. So I have 10 multiplied by 10, so I have 100 data points. Or I mean 100 experiments that I'm gonna do. Again, this is with the assumption that 10 is okay. And then you are repeating this for 5 parameters, so I have 500 experiments that must be done so that I can get the results, taking into account everything. You can imagine if you do this for 7 or 8 parameters, if you have another system that contains or includes 7 or 8 parameters, this would be even more and more. So you're talking about 700 or 800 experiments. And if you decide to go for 15, 20 data points, so this is an exponential increase in the number of experiments that you need to do. So it's going to be a very, very, very wasteful or time wasteful process. But let's say we have a lot of manpower, we have many people who want to work on this, and they are willing to do these 1,000 or 2,000 experiments to get these data points. We still have other questions that may make this not a valid approach. One question is, we said, or we assume that we are gonna change one parameter and keep the other constant. But is this really a possible thing? If for instance I want to change the density, how can I change density without changing the viscosity and the diffusion coefficient? Changing density can be done either by changing the temperature, which will affect the diffusion coefficient and the viscosity, or by changing the fluid itself, which will definitely change the viscosity and the diffusion coefficient. So I cannot say, theoretically speaking, I can say that I can keep everything constant and change one parameter, but practically speaking, this is not possible in our case. I can never change the density without changing the viscosity and the diffusion coefficient. And let's say, for the sake of argument, that we could do this with a magical way, that we could change the density without changing the viscosity and the diffusion coefficient. I now have relations, or I have studied the effect of each one of these parameters on the diffusion coefficient, on the mass transfer coefficient, but I couldn't study the combined effect of changing the parameters. So let's say I have a case where I have 2 parameters or 3 parameters that change simultaneously, and this change might not be like predict, I have a lot of options to change the parameters. Maybe one increases, other decreases, both increase, 3 increases and 1 decreases. You have like a lot of options. So can we predict this with the experiments? So if you think of how many experiments you need to do with all the combinations of increasing and decreasing of all the 5 parameters, this is gonna be an endless number of experiments that you have to do. So it's not a practical approach to follow, although it seems logical in the beginning, but practically speaking, there are a lot of drawbacks and a lot of issues that you would face if you follow this approach. And that's why the solution was to use the dimensionless parameters like Reynolds number, Nusselt and Prandtl number in heat transfer, and here we use Reynolds number and other dimensionless numbers that we will use. But the dimensionless number, and the idea of the dimensionless numbers, is to group all these parameters, and instead of having 6 parameters, the mass transfer coefficient and the other 5 parameters, and instead of having them as 6 parameters, you group them into 3 dimensionless parameters. Each one of them is a group of some of these parameters. So these dimensionless parameters reduce the number of experiments that you do. So we said we have here, in our case, we have 2 parameters affecting 1 parameter, which are the dimensionless parameter. So the number of experiments that you need to do are much more, much less than what you should do in case of having 5 parameters. Also, the dimensionless parameters like Reynolds number, because it's a famous number and we already know it from heat transfer and fluid mechanics, Reynolds number is combining the parameters together. So if you change the density and the viscosity, or you change any one of them, it doesn't matter. As long as you have a value of Reynolds number, it doesn't matter that this number is big due to the low viscosity, high density, if it's due to the high velocity. It doesn't matter what is the parameter that is causing this. The value of Reynolds number itself is what affects the mass transfer coefficient. So this like takes out a lot of details that you don't want to go into. This gives you a number that just affects Reynolds number as a dimensionless number, regardless of the values of each one of the specific parameters inside this. So this is a genius thing. And one other thing, as we said earlier, or in the previous video, that the dimensionless parameters have physical meaning, and this is what we will see here, that we will have some dimensionless parameters that are not meaningful, and we will generate a meaningful dimensionless number from them. But the point is that they have a meaning, they reduce the number of experiments that you need to do, and they save a lot of time. They give you a physical meaning to the system that you are dealing with. So this is a very, very, very important thing to understand, why we bother to go and do all these mathematical derivations and to get the dimensionless parameters and do this whole mathematical exercise. This is important because without it we cannot do the experiments. We cannot generate results that we can use to get or predict the relation between the parameters and the mass transfer coefficient. Now comes the question, how can we get the dimensionless parameters? This is what we are going to talk about next time when we talk about Buckingham pi theorem. So I'll see you then, inshallah. Goodbye.